Hey everyone, this is Professor Turner with Purdue Polytechnic, and today's video topic for Fundamentals of Electromagnetics is an introduction to transmission lines. We've briefly already gone into a little bit of transmission line theory and its application to bounce diagrams, but in that treatment we only looked at DC and pulse responses, and so now what we want to really understand is what happens if I apply an AC signal to a transmission line that is then connected to some sort of load device. And we want to be able to predict what the voltage and current along the transmission are, and then also what the voltage and current at the load are. So that's what we're going to be doing in this video and then the next two video sections. So I'm going to put the topic objectives for all the videos up here because really the next three videos are just one long video broken into three smaller parts. And in these three videos, we're going to address these following learning objectives. And the first is that we'll develop a set of equations that describe the propagation of electromagnetic energy in terms of voltages and currents along a transmission line, and these are called the AC wave equations. We will then use the AC wave equations to develop some parameters that characterize a transmission line, and we're going to the first is going to be a characteristic of a transmission line called the characteristic impedance of a transmission line. We're then also going to use those wave equations that we develop to calculate what happens when a traveling wave encounters a impedance boundary, and we've already talked about this concept of the reflection coefficient. So we'll more fully develop the concept of this reflection coefficient. We're going to see what the consequence of having a reflection coefficient on an AC waveform is. We have a little bit of an idea from our bounce diagrams, but we're going to look at what's called the standing wave pattern and the voltage standing wave ratio of a transmission line in which a reflection occurs. We are going to create a simplification of the transmission line and a load device, and we're going to call that the input impedance of the transmission line and load. And we'll show how to calculate different input impedances for terminated transmission lines. And by terminated T-lines, we just mean transmission lines that are connected to loads. We're going to then look more at these specially terminated transmission lines. There's some certain cases that are more useful than other ones, and we're going to look at those, and we're going to look at how we might utilize those to design circuits in the future. And once we've done that, we're going to fully solve the voltage and current wave equations to determine the voltage and current along a transmission line and at the load. And finally, we'll wrap up by talking a little bit about power transfer from a source to a load on a transmission line. So those are the topic objectives. I just want to give you a big picture idea of what we're going to do. So the first thing is we're going to take that distributed parameter model that we already have, where we've got R prime, which is the distributed resistance, and L prime, which is the distributed inductance, and then of course we've got the shunt elements, C prime, distributed capacitance, and G prime, which is distributed conductance. So we're going to start with this, and we're going to see how the voltage and current waveforms propagate in an AC system along this differential element of transmission line using Kirchhoff's voltage law and Kirchhoff's current law. Once we've solved that, what we're going to do is we're going to connect a load to this circuit, and we're going to see what happens when we've introduced an impedance boundary here between our transmission line and our load, and we'll analyze that for a variety of cases. Once we've solved that, what we're going to do is we're going to go ahead and connect a generator with its series impedance, which introduces a second impedance boundary. And all of this we're doing for AC sinusoidal quantities. So that's big picture what we're going to be covering in the next three video series.